That was a quick 5 minutes. All right, so here is Theorem 14. It says if we have F, a subset of K, a subset of L fields, all right? In other words, we have K over F, right? And L over K, right? L is an extension of K. K is an extension of F. In this context, then, the degree of L over F is equal to the degree of L over K times the degree of K over F. In other words, an extension, degrees are multiplicative. And, oh, this is also, if one of these is infinite, then both sides are infinite. And he's got a nice,
yeah, that makes sense.
nice picture.
You can't contain an infinite field into a finite
Yeah,
field, and you can't. Well, how do you get the converse though? What if L is infinite?
If L is infinite, then L over K is also infinite. I mean, if L over K is infinite, L over F is also infinite. So here's the other picture he has of this. Is like this is I think he thinks of this as L over F, right? The dimension here is K over F. The dimension here is L over K. So to get the dimension from here to here, we multiply this by that. And I proved this in your previous course. Believe it or not, I believe I did. But essentially the proof is this. If K is equal to the span, the F span of 1 alpha, alpha to the, well, excuse me, let me just say alpha 1, alpha 2, alpha n. And if L is equal to the span over K, the K span of beta 1, beta 2, beta m, then you can show that the set alpha I, beta j, such that 1 less than or equal to I less than or equal to n, 1 less than or equal to j less than or equal to m, you can show that that is a F basis of L over F, right? Or just say it's a basis of L over F. So that's essentially just the proof is just that. You just prove that if you multiply the bases, you get a basis. Corollary 15. Suppose L over F finite extension and K subfield of L, any subfield of L containing F, i.e. F is a subset of K is a subset of L, right? Then the degree k over f divides the degree of k over L. Excuse me, over L over f. Proof. This is immediate. Okay.
Oh, yeah, it actually is.
Right.
Because if the degrees are, if by theorem 14, they're
Mhm.
multiplicative,
Yeah.
they have to be divisible.
Exactly. The theorem 14 gives us the divisibility condition, just like that. Yeah. I'm an idiot. I forget which side's the corner. I had the camera moved over to the other side of the board. Flipping that screen just messed with my head. Anyway. So, example 1. So square root of 2 is not an element of Q adjoin alpha where, basically he's got alpha cubed minus 3 alpha plus 1 equals to 0. He says alpha is the root. Oh, fine. Alpha root of x cubed minus 3x minus 1. All right. But here's how to argue that, right? I mean, there was a separate. Of course you could just. Let me shut up. So the degree of Q alpha over Q is 3, right? The degree of Q adjoining the square root of 2 over Q is 2.
They're not divisible.
Right, so you cannot have the situation Q subset of course, Q is a subset of Q adjoined root 2, right?
Yeah.
But this is not a reasonable scenario because, as you said, 2 does not divide 3. So, right. And this beats the pants off trying to prove directly that, well, I don't know, I guess you could also just plug root 2 into this, right? And if you don't get 0, then it's not a root, is it? Well, sorry, you have to be aware of my comments. My comments this time of day start getting to be stupid, so we have to remember Dr. Cook comments stupid in the 4th hour of his lecture in a given day. So keep that in mind. Where was I? He said, it's not so easy to prove directly that the square root of 2 cannot be written as a rational linear combination of 1 alpha and alpha squared. Like, is it obvious that here's the question, can you write square root of 2 as like a plus b alpha plus c alpha squared? Now, that's a harder thing. It seems plausible, some chance you could do that. But no, you cannot, because this is an element of Q adjoin alpha, right?
Yeah.
And so if you could write root 2 there, then that would mean that Q adjoin root 2 is a subfield of Q adjoin alpha,
Yeah.
which then contradicts the...
I was like, yeah, beat 0.
So this, the major application of the thing we're looking at right now is when it doesn't divide. Like that's, you get proofs of irreducibility of things in really sneaky kind of sideways ways. He says, okay, so let the sixth root of 2 be the usual positive, sixth root. Then, of course, we have that q join the sixth root of 2 over q is what? This is a degree 6 extension, right? Because the minimal polynomial here is x to the 6th minus 2, All right. And then since the sixth root of 2 cubed is what? Root 2, right? Yep. Square root of 2. We have, so what does that tell you? That tells you that square root of 2 is an element of q adjoin the sixth root of 2, right? Hence, q adjoin the square root of 2 is a subset of q adjoin the sixth root of 2. Well, no, not because it's divisible, because this shows it. If you have the element that is extending by in it, and they have the same,
That's what we can do over that side.
So we can have so here's the picture. We've got q adjoin the square root of 2. We've got q adjoin the sixth root of 2, right? So again, this, and so let me write this like a different way. So we have q adjoin the sixth root of 2. We've got q adjoin the square root of 2, and we've got q. All right. So this is a tower of fields, and we can just write the degree on the thing. So like this is a degree 2 extension. This is a degree 3 extension. I guess that's the thing we didn't know already, isn't it? Right? That the extension of q adjoin root 2 to q adjoin the sixth root of 2 is degree 3. Right? Maybe that's not immediately obvious without this degree extension formula stuff we're dabbling in at the moment. So, but what this also shows you is that the degree of the minimal polynomial, right, of the sixth root of 2 over q adjoin root 2 is 3. So, like the minimal polynomial of the sixth root of 2 over the field q adjoin root 2 is some third order something. I mean, maybe I can actually work it out. I mean, this is a simple enough example. I might be able to make that explicit. Let's see here. We also know, I mean, this is not done, right? Incomplete. We know that the minimal polynomial of the sixth root of 2 over q is x to the sixth minus 2, right? And we know that that factors as x to the x cubed squared minus the cube root of 2, right? Squared? No, wait a minute. Sixth root of 2. Nope, I'll get it eventually. What do we want? We want this. Oh, so this is minus, yeah, okay, this minus this squared, right? Which, of course, gives us x cubed minus root 2, x cubed plus root 2. We're factoring where, not that's, I'm factoring over
Well, you're
q join root,
Q6.
q join,
with
yeah.
Q.
But I'm factoring in q, I'm using coefficients from q join root 2 at the moment.
Yeah.
So I believe what you put here is just this minus root 2. Like that's the, I think that's the minimal polynomial in question. That's the degree 3. Yeah, that's the degree 3 minimal. The degree 3 irreducible so here's the thing. This proves that that is irreducible over q adjoin root 2. That's kind of cool. We got plenty of theorems about irreducibility over q or something else, but q adjoin root 2, that's, you know. He says, note that showing directly x cubed minus root 2 is irreducible over q adjoin root 2 is not entirely trivial. So that's something. So what do we mean? So definition. Extension k over f is finitely generated if there exists alpha 1, alpha 2, alpha k, such that k is equal to f alpha 1, alpha 2, alpha k, right? In that notation, f alpha 1 comma L2 alpha k is notation for the smallest set, which contains, you know, the base field f as well as the extension elements alpha 1 through alpha k. This is not to say that k is finite extension. So like q adjoin pi is a finitely generated extension because I'm just extending by pi. But I think you could, don't ask me to do this, but I believe you can prove that, for example, the real numbers are not a finitely generated extension of the rationals.
Well, no, because irrational set, infinite set.
So are the reals.
Huh?
So are the reals.
So are the rationals.
Yeah, I'm saying that, what I'm saying is the reals are not finitely generated over the rationals, but you're starting with an infinite rational. The rational sets is infinite.
Yeah, but I was saying, like, there's a one-to-one correspondence. And if you take the irrationals out, there would be, there's no one-to-one correspondence with the irrational numbers. You can map Q. There's a bijection, not bijection. There's a one-to-one map from N onto Q.
That is true. The rational numbers are countable. The reals are not. And
So, yeah, the reals without the irrationals are counted. They have a finitely generated.
yeah,
That field can't be extended because.
that is most likely the heart of the proof of what I'm claiming. So, but I don't know. Okay, so another way to look at f of alpha comma beta is f of alpha. You take the field f of alpha and then you extend by beta.
Okay.
So we can view, he says the proof, it follows by the minimality of the fields in question. So basically, this field contains alpha and beta and f, right?
Yeah.
This field, the inside field, contains f and alpha, right? but then if you extend by beta, it also contains beta. So this is the smallest field, which contains F alpha and beta. Let's see here. So he's basically arguing that the proof, there's a couple of different parts to it, but part of the proof is that by minimality, F of alpha extended by beta has to be a subset of this, because this thing contains alpha, beta, and F. And as such, it has to be a subset of the minimal field containing alpha and beta. Well, he uses minimality in the other direction as well. So there's the minimality of this extension, then there's the minimality of that extension, and when you put them together, you get this is a subset of that, and that's a subset of that, which gives you equal. Yeah. So there's two different notions of minimality at play here. There's the minimality of the double extension, if you will, and we'll call one the double extension, the other compound extension. I don't know what the different names of these things should be, but both of these, I'll put it in a sentence. F adjoint alpha beta is the smallest field which has F as well as the elements alpha and beta. So since this contains F, alpha, and beta, it has to be a subset of that. This, on the other hand, is, first of all, this is the smallest field which contains F and alpha.
And you're extending by beta.
All right, and then this is the smallest field which contains F of alpha as well as beta.
Which means F of alpha.
Which means that this is a subset of that. I mean, it really, okay, fine. It's just, there it is. All right, so so you notice what we have here is that F is a subset of F of alpha is a subset of F of alpha of beta, right? I mean, that's clear from, the thing is that this is clear from, see, this is clear from the, from the very construction of these things. And so what does this tell us? This tells us that the degree of F, but this of course is equal to F alpha comma beta. So F of alpha comma beta over F is equal to the degree of F of, let's see here, of F alpha comma beta, alpha comma beta over F of alpha times the degree of F of alpha over F. And, similar calculations, if you have a chain of fields, right, like F1, F0, a subset of F1, subset of F2, subset of Fk, whatever, then the degree of Fk over F0 is what? It's equal to the degree of Fk over Fk minus 1 times the degree of Fk minus 1 over the degree of Fk minus 2, until finally you get down to the degree of F2 over F1 times the degree of F1 over F0. So it's just extending multiplicity, the multiplicative degree idea to like multiple extensions. This is something we can do. And anyway. I know, I just... try to keep it moving here. So here's some examples. All right, so let's look at, I'll look at his second example. Here we've got Q adjoin square root of 2 and square root of 3 over Q. So he says that the Q adjoin 2, 3, right? Over Q adjoin root 2 is at most 2, the degree of this extension. Well, he says since root 3 is degree 2 over Q, that's why the degree is at most 2, right? Since he says it'll be precisely 2 if x squared minus 3 is irreducible over Q adjoin root 2. Since the polynomial is of degree 2, it is reducible if and only if it has a root, if and only if that is root 3 is an element of Q adjoin root 2. So let's look at how, so we're about to, so if x squared minus 3 is irreducible over Q adjoin root 2, then that would give us that this is a degree 2 extension. So I think he was about to give just a proof that it's irreducible over that. All right, so but it's over Q adjoin root 2, notice. So I mean, it's yes, this is irreducible over Q, true, but we're worrying about over Q adjoin root 2. That we don't know. So x squared minus 3 is reducible. He says only if square root of 3 is an element of Q adjoin square root of 2. Yeah, I mean, because we know that this, we know how to factor that as the thing, right?
Yeah, that's what I was thinking.
You're right. So because of this, because we know the larger world of factoring with real numbers and so forth, we know that. And we also know that, this is a unique factorization domain, so like, that's it. So the only way that this could be reduced is if this square root of 3 was in Q adjoin root 2, right? So the question is, can you solve the equation Q adjoin root, can you find square root of 3 is equal to A plus B square root of 2 for some choice of A and B? You say no, but why?
Because for A and B in which set? A and B what set?
for A and B rational?
Yeah, no.
How do you know no?
One, it's not squared. Two, you can't multiply an irrational number by a rational number and get a rational number back. These are not the same sets. An irrational times irrational wouldn't give you, like, you can't multiply.
Well,
that.
irrational times rational gives me irrational. Irrational plus rational is irrational. Irrational equals irrational. Okay.
I see your point.
But I mean, you're not, well, so we need, there's a theorem we already know, which is that square root of 2 is not rational,
Yeah.
right? So if we can use that, so here's what we do. We just square this equation.
Okay.
Which gives us, of course, a squared plus 2b squared, right? Plus 2ab root 2.
Sure.
Okay, now we know that 1 comma root 2 are linearly independent because those are the basis for the Q adjoin root 2 extension, right? We know irreducibility of, okay, so we again get that 3 has to be equal to a squared plus 2b squared, and 0 has to be equal to 2ab from this equation. Can we solve that?
No, because A or B have to be, so given your choice, this is what I'm thinking, given your choice of A and B being 0, one of them having forcing to be 0.
Right.
If it's A, that means 3 is an odd number, B would have to be an even number.
Well, a and b are rational, so I
Okay.
don't know what you mean, but yeah.
You're right. You get either 3 equals 2b squared or 3 equals a squared. 3 is not squareable into the rational.
Right, so, yeah, exactly. So this gives us 3 over 2 is b squared, or this gives us, yeah, a is equal to plus or minus square root of 3. So this gives b is equal to plus or minus square root of 3 over 2, which, of course, those are not rational solutions. Therefore, indeed, x cubed minus 3 is irreducible over q adjoin root 2. What does that tell us? So, so we just got that the minimal polynomial of square root of 3 over q adjoin. Why am I writing all this? I'm a dummy. Let me just get to the point. So the degree of the extension q adjoin root 2 and root 3 is what? It is apparently 2. So the degree of q adjoin square root of 2 comma square root of 3 over q adjoin square root of 2 is 2. And of course we know that the degree of q adjoin root 2 over q is 2. So what does this tell us about the degree of q adjoin root 2 root 3 over q?
Okay, so that's 2, that's 2, that has to be 4.
Exactly. So it's exactly, it's 2 times 2. So much writing. And that proof that, the extension of an extension, the proof of the multiplicativity of degrees, that proof also instructed us on how to construct the basis for the extension. It said you just multiply the bases.
Yeah.
So we had basis like 1 and, 1 and root 2 for, for q adjoin root 2. And we could look at this, we would have basis 1 and root 3 for for this one. Excuse me, for this one. Okay. That's a basis because we're extending by root 3, right? So, right. Anyway, so when you multiply those, what do you get? You get 1, square root of 2, square root of 3, square root of 2 times 3, which is square root of 6. So there you go. That's the Q basis for this guy. Son of a gun. Theorem 17, I will just say, I won't write, all right? Theorem 17 says that an extension is finite over F if and only if it is generated by a finite number of algebraic elements over F.
It is only generated?
It is extension K over F is finite if and only if K is generated by a finite number of algebraic elements over F. I might have added the word only, but sorry. More precisely, a field is generated over F by a finite number of algebraic elements of degrees n1 through nk is algebraic of degree. Okay, so
Extension field is over F. Extension is finite over F if and only if K is generated by finite algebraic elements.
right.
Okay.
But more than that, it's like if you have K is equal to F of alpha 1, alpha 2, alpha, let's say K, well, I'll say S, then the degree of K over F is less than or equal to like N1, N2, Ns, where the degree of F of alpha S, alpha I over F is equal to N sub I. So like whether or not, so when you extend by a bunch of elements, the maximal degree that you can get is the product of the degrees of the elements by which you're extending. But that maximality is only attained in the case that the elements you're extending by are in some sense independent. Like the example we just worked through is one of these examples. Square root of 2 and square root of 3, they're minding each other's business. So when we extend by an element of order 2 and another element of order 2, we got a degree 4 extension. But if we were to extend by two different things which were somehow interrelated,
Like a scalar of each other?
like a degree 2 and a degree 4 element,
Yeah.
we might not get a degree 8 extension if that degree 2 element was already in the degree 4 extension. But it can get more complicated than that. But yeah. Corollary 18. This one's actually useful. I mean, all of these are useful as you're doing certain homework problems, I suppose.
People walk into the math lab and everybody's staring at me doing these problems. They're just like, well, they were staring at you, so I want to stare at you.
You're like, it's just algebra, man.
I'm not your professor.
No. Corollary 18. Alpha, beta, algebraic over F. Then alpha plus or minus beta, alpha beta, and alpha over beta and, well, alpha inverse, I'll throw that in for alpha not equal to 0, obviously, are algebraic over F.
Alpha and beta not equal to 0, right?
Yeah. So the proof is essentially just the following. F adjoint alpha comma beta contains, alpha plus or minus beta, alpha over beta, and alpha inverse, right? And if this is, so alpha is algebraic, beta is algebraic, so F alpha comma beta is algebraic. Therefore, all of these elements are also algebraic.
Does not need beta inverse?
What's that? I mean, well, beta inverse is, alpha is an arbitrary thing, so,
Okay.
technically you could just leave it like alpha over beta and say alpha equal to 1. I don't know. Anyway, the point is the sum difference product fractions or even just reciprocals of elements you're extending by are necessarily algebraic if the elements themselves are algebraic over F. So it's good to know. Let's see here. Corollary 19 says that if L over F is extension, an arbitrary extension, not an algebraic extension, then the collection of elements of L that are algebraic over F form a subfield of L. Let's call these K, form subfield of L. So we've got F is the base field, K is the set of algebraic elements of L over F, and L is up here. So, if L is not an algebraic extension, then there could be elements which are not algebraic in it. And so, yeah. So, example of that. He says, consider the extension of the complex numbers over the rational numbers. Then you let Q bar denote, it's a subset of C. So this is going to be all algebraic elements of C over Q. All right, this is a subfield of the complex numbers, right? And it's an infinite subfield. To see that it's an infinite subfield, it suffices to show, well, check this out. So, of course, the nth root of 2, right, is an element of these guys. Agree?
Yep.
And the degree of Q adjoin the nth root of 2 over Q is n. But you can make that n as large as you like. And so, Q bar it contains the nth root of 2 extension as a subset. So clearly it's infinite dimensional over Q, right? So, and yet, so this is a lot of numbers, these algebraic numbers.
Yeah.
A lot of numbers. And next he says, look at Q bar intersect R. Look at the reals intersect Q bar. What does that give us?
R again?
That gives us the subfield of the reals consisting of elements that are algebraic over Q. Real numbers, algebraic over Q, right? So like, for example, I is an element of Q bar, but I is not an element of this, right? What's he got to tell us here? He's like, well, the field Q is, as you were saying a second ago, countable. The number of polynomials over rationals of any given degree is therefore, degree n is therefore also countable. And since polynomials have at most n roots in R, the number of algebraic elements of R of degree n is countable. And finally, the collection of all algebraic elements of R is countable. The union of countable sets is hence countable. Since R is uncountable, there exist, in fact, many elements of R which are not algebraic, right? In particular, the subfield Q bar intersect R of algebraic elements of R is a proper subfield of R. So, I don't know if he's saying that this, I haven't quite figured out, is Q bar countable or not here? I'm not sure. I think it might be, from what he's saying. Well, I'll just leave it at that. I'm not sure what to say more about that. The next theorem is that if L over K algebraic and K over F algebraic, then L over F is algebraic. So the algebraic extension of an algebraic extension is algebraic. All right. And then the final push in this section is if you have, so the last thing that's discussed in this section is if we have like K1 and K2 are subfields of, let's say, an extension, say E, right? Then K1, K2 is a subfield of E. So he defines the product of two fields. And his definition is, it's called the composite field. It's the smallest subfield of K, which contains, in my case, E, smallest subfield of E, which contains both K1 and K2. All right. And the big event here is proposition 21, which says that the degree of K1, K2 over F is less than or equal to the degree of K1 over F times the degree of K2 over F. So we saw equality in that example where we adjoined root 2 and root 3, right?
Yeah.
So really, you could, and as an example of this, Q adjoin root 2, Q adjoin root 3, product field is actually given by Q adjoin root 2 and root 3. But anyway, so we will use this proposition in future sections. It'd be good for you to read the rest of the section, but I'm going to try to move on next time because, as you know, our time is limited. You could say we got to run.